Here's the third video on KSP, solubility product constant. One thing, or a couple things here. First thing, some students have a tendency to think that this number is the solubility. Okay, remember, it is not the solubility of the substance. It's not how much can dissolve. It is the product of the ions to their powers. Okay, so it is not the solubility of it. The other thing is you got to be careful looking at KSP values and saying, okay, one thing's more soluble than another. Okay, so for example, these two. You can't necessarily look at these two and go, well, they have the same KSP. They're actually not in real life, but I changed them. They're pretty close to start with. But you can't look at these two and say they have the same solubility because they don't split into the same number of ions. Okay, if they split into the same number of ions and they have the same KSP, then you could say which one is more soluble or the same solubility. What I mean by that is this one would be the concentration of Mg plus 2 times the concentration of CO3 negative 2 would be that KSP, so just 2 ions. This one is the concentration of lead ions times the concentration of bromine ions squared. So if you think about when we talked about in the previous video how to get solubility in water, we put in an X for this one, X for this one. This one would just be an X squared. It's supposed to be an X. That'd just be an X squared. So you would take the square root of that, and you'd figure out the solubility. This one would be X times 2X squared, which ends up being 4X cubed. So you would divide this by 4, take the cube root, going to give you a much smaller answer. This is going to be more soluble in water than this is going to be. Okay, now, if they split into the same number of ions, you can look at the KSP value and just figure out which one is more soluble. So previous video, tried to figure out solubility in water. So if I want to know the solubility of this compound in water and I know it's KSP, well, I said it's KSP 3.8 times 10 to the negative 9 equal to concentration of calcium. I can put in X4 times concentration of carbonate. I can put in X4 is X squared. I can get the square root. I can figure out the solubility of this compound in water. Now, what if I try and put this into a solution that already has some calcium ions in it, or already has some carbonate ions dissolved in it? What's going to happen then? So we can figure out if there's already a common ion in there. So I'm going to go down to, this is exercise 4. Solubility and common ions. So I want to know the solubility of calcium fluoride in a 0.025 molar sodium fluoride solution. So not in water. Okay, not in water. So first thing, always write down what's happening. You got some solid calcium fluoride. Okay, again, we're not putting it in water. It's in a solution that has some sodium ions and some fluorine ions in it. Splits into calcium ions plus 2 moles of F negative ions. So if I was trying to figure out the solubility in water, I'd put in an X right here, a 2X there, set those equal to the KSP. Okay, this one would have to be squared, and figure out the solubility in water. But now we already have a solution that has some sodium fluoride in it. So we have a solution that's water, but it has sodium fluoride, which is completely soluble. So it's got some sodium ions in it and some fluorine ions in it. And both of them are 0.025 molar. 0.025 molar sodium ions, 0.025 molar fluoride ions. Well, the sodium ions don't affect anything. Okay? Anything with sodium in it is always soluble, so it's always split apart into ions. But these fluorine ions in there, since there's already some in here, it's going to affect how much of this can dissolve. It's going to make it be a little bit less than if it was pure water. Because multiplying these together can't go above the KSP. And since we already have some in there at a pretty high concentration, we're not going to be able to put a whole lot more of this in there. So what we're going to do is say, well, this is 0.025 molar. Okay, you don't have to double it or anything like that. That's how much is in the solution. Okay, and then we're going to add calcium carbonate as a solid to it and see how much can dissolve. So we're just going to put an X in right here for calcium and see if this concentration is already this much, how much more calcium ions can we put in there before the solution is saturated. So we'll say our KSP equals X times 0.025 molar. But the 0.025 needs to be squared. put in our KSP, which is 4 times 10 to the negative 11th. So we're going to square that, divide over to this side. Square the 0.025, divide it over here, and our x. Now our x is 6.4 times 10 to the negative 8th molar. 6.4 times 10 to the negative 8th molar. That is our concentration of calcium ions. Well, since calcium ions are in a 1-to-1 ratio with the compound, that is our concentration of calcium fluoride that can dissolve. That's as much calcium fluoride as we can dissolve in solution if there's already that many fluorine ions in there. Can't go above the KSP value, so you can only get that many more, that much more concentration dissolved in there. Sometimes you'll get compounds like, say they'll give you like magnesium hydroxide and say, okay, we're going to dissolve that in some acid. So you got to think about, hey, what's going to react? What's the acid going to provide? Well, acid's going to react with OH negative ions, remove those. Okay, so we'll do some problems like that down the road here. Let's do one more problem. This is KSP and the reaction quotient Q. So remember, Q is when we're not at equilibrium. We're trying to figure out if we are at equilibrium or not. Okay, so if Q is less than KSP, that means the reaction needs to move in the forward direction. In other words, get more of the products. If Q is equal, the system's at equilibrium, that means the solution is saturated. It can't dissolve any more of the solid. If Q is greater than KSP, it's supersaturated. We got more stuff in there we can have. Okay, and that means you're going to get a precipitate. It's going to move back to make more solid. Stuff's going to come out of solution. Okay, so if I added some more of one of these ions in here, either lead ions or chloride ions, that would start to precipitate out more of the stuff that's in there. Okay, it's already saturated. It's got as much in there as it can dissolve because there's something on the bottom. So what I want to know here is if a precipitate will form in this reaction. Okay, just trying to figure out if a precipitate will form. Again, this is exercise number 5 here. So we're going to mix some cerium nitrate. Okay, that's completely soluble, and there is 750 milliliters of essentially 0.004 molar. And we're going to mix that with some potassium iodate, again, which is completely soluble. There's no KSP value for either one of these. They completely dissociate, completely dissolve. And that is 300 milliliters of 0.02 molar. Well, it's asking you about this. So that's going to be our precipitate, cerium iodate. Potassium nitrate is going to be spectators. We're going to make some cerium iodate here. And it wants to know if precipitate will form. Okay, so let's think about cerium iodate. So this reaction is going to make cerium iodate, which will form cerium plus 3 ions plus IO3 negative ions. And it'd be 3 moles of those. So if we think about our KSP, again, we can't go above the KSP. The KSP, when we multiply this times this to the 3rd power, so concentration of cerium ions times concentration of IO3 negative ions to the 3rd power, this product can't go above the KSP. If it does go above it, we're going to have precipitate. If this value is less than KSP, there's going to be no precipitate. If we're right at KSP, it means that we're at equilibrium. It's going to be exactly saturated. So if you think about what we need to know the molarity of these ions and those ions and plug them in. So, and they're not related, they're individual because they're coming from 2 different solutions. Okay, the cerium ions are coming from this solution, so that's going to be a certain moles. These are coming from this one, so that's going to be a certain number of moles. They are mixed together, so we have to get the total volume of the solution. But if we multiply this times this, our moles would be 0.003 moles. If we multiply this times this, our moles are 0.00. I don't have that. Something moles. So it'd be 0.006 moles. So if we, again, this is moles, and this is moles of IO3 negative ions. This is moles of Ce+3 ions. We're not worried about nitrates or potassium ions. We need to get this into molarity. So the molarity would be this divided by the liters, which is 750 plus 300. Okay, 1050 or 1.05 liters. Divide this by 1.05 liters. And this molarity is 0.00286 molar. Again, that's Ce+3. And this one is 0.00571 molar. Again, that's IO3 negative. So we're going to take those, plug them into our KSP, see if it's bigger or smaller. Excuse me, plug them into this, which essentially would be Q, because we're not at equilibrium. So we'll plug this in over here, 0.00286. Don't forget the IO3 negative will be cubed, 0.00571 cubed. We do that, we get a Q of 5.34 times 10 to the negative 10th, okay, which is bigger than the KSP, which means there's more of these that can be dissolved. Okay, so it's not by much, greater than KSP. So yes, there is a precipitate. Okay, you would get some precipitation, but not a lot of precipitation because we're not much above the KSP value. Sorry for a long video.